Look up at the night sky. What do you see? A vast, endless sea of stars, galaxies, and mysteries stretching beyond what our eyes can even comprehend. But here's something that might make your jaw drop. That breathtaking expanse isn't just sitting still. The universe is actively growing, stretching, expanding faster than we ever imagined. And the craziest part, the farther we peer into the cosmos, the more we realize this expansion isn't slowing down. It's speeding up, defying everything we thought we knew about the fabric of reality. What if I told you that space itself is stretching, carrying galaxies away from each other like dots on an inflating balloon? That distant galaxies are racing away from us at speeds so immense, their light may one day vanish from our skies forever. This isn't science fiction. It's the mind-bending truth about our universe, a cosmic dance of dark energy, gravity, and forces we're still struggling to understand. And today, we're diving deep into 30 astonishing facts about this relentless expansion, facts that will reshape how you see the cosmos. From the echoes of the Big Bang to the mysterious dark energy pushing the universe apart, each revelation is more incredible than the last. You'll discover how scientists measure the universe's growth, why this expansion could rewrite the fate of everything, and what it means for the ultimate destiny of all existence. So buckle up, we're about to embark on a journey across space and time, unraveling the secrets of a universe that's literally racing away from us. Trust me, by the end, you'll never look at the night sky the same way again. In 1929, Edwin Hubble made a discovery that shattered our understanding of the cosmos, one so profound it changed astronomy forever. While observing distant galaxies through the powerful Hooker telescope at Mount Wilson Observatory, he noticed something bizarre. Nearly every galaxy wasn't just moving, it was racing away from us. But the real shock came when Hubble plotted their speeds against their distances. The farther a galaxy was, the faster it seemed to be fleeing. This wasn't random chaos, it was a pattern so precise it screamed a single, staggering truth. Space itself was stretching, carrying galaxies apart like raisins in rising dough. Hubble's data didn't just hint at an expanding universe, it proved it. His now famous graph, a simple scatter plot of galaxies, showed a near-perfect straight-line velocity shooting higher with distance. That straight line became Hubble's law, the cornerstone of modern cosmology. Imagine throwing a rock into a still pond. The ripples spread outward with distant ones moving faster. Now picture that, but with galaxies embedded in spacetime itself. That's what Hubble saw. His calculations even gave us the Hubble constant, a number that tells us how fast the universe grows over time. But here's what makes this even wilder. Hubble's discovery wasn't just about motion. It was evidence that the universe had a beginning, a moment when everything erupted from a single point. If space is stretching now, rewinding the tape meant it was once unimaginably dense and hot. That insight planted the seeds for what we now call the Big Bang theory. Yet Hubble himself hesitated to call it that. In his papers, he cautiously described it as a general tendency of galaxies to recede. He couldn't have known his careful measurements would become the first brushstroke in humanity's grandest cosmic portrait. And those original black and white photos from Mount Wilson, they weren't just data, they were glimpses into a dynamic, evolving universe, one where the very fabric of reality was in motion. Hubble's law didn't just reveal the universe's expansion, it handed us a key to unlocking its past and its fate. Little did he know, his work would set the stage for an even bigger mystery lurking in the darkness, the force we now call dark energy. Einstein called it his greatest mistake, but history would prove him wrong in the most spectacular way. When Albert Einstein was working on his theory of general relativity in 1917, his equations kept predicting something unsettling, a universe that couldn't sit still. The math insisted space should either collapse under gravity or balloon outward, but scientists at the time were convinced the cosmos was eternal and unchanging. So Einstein did something radical. He added a fudge factor to his equations, a mathematical term he called the cosmological constant. This mysterious number acted like an anti-gravity force, balancing the equations to produce the static universe everyone believed in. The irony, less than 15 years later, Edwin Hubble's telescope observations proved the universe wasn't static at all. It was expanding. Einstein realized his cosmological constant had been unnecessary, dismissing it as the biggest blunder of my career. He reportedly crossed it out of his notes with a frustrated stroke of his pen. But the story doesn't end there. Fast forward to the late 1990s when astronomers made an even more shocking discovery. Not only was the universe expanding, but the expansion was accelerating. And suddenly, Einstein's discarded constant wasn't looking so foolish after all. That's because the cosmological constant turned out to describe something very real: dark energy, the mysterious force pushing galaxies apart at ever-increasing speeds. Einstein's mistake had been ahead of its time by nearly a century. Today, original manuscripts from his notebooks show scribbled equations where he wrestled with the idea, crossing out the constant only to later reconsider its implications. Those yellowed pages tell the story of a genius who glimpsed the truth before the evidence existed to prove it. What makes this twist even more fascinating is how it reshapes our understanding of scientific progress. Einstein introduced the cosmological constant not because he believed in it, but because he was trying to force his equations to match the accepted view of the universe. When Hubble proved that view wrong, Einstein abandoned the idea only for modern cosmology to bring it roaring back. Now, dark energy makes up roughly 70% of the universe's total energy, making Einstein's blunder one of the most important concepts in physics. The cosmological constant's journey from rejected idea to cornerstone of cosmology shows how science often moves in loops rather than straight lines. Sometimes the answers are hidden in plain sight, waiting for the right moment to reveal their brilliance, and perhaps the most humbling lesson: even the greatest minds can't always recognize their own breakthroughs. Picture a police siren wailing past you on the street. As it moves away, the pitch drops lower because the sound waves stretch out. Now imagine that same principle applied to light across the universe. When astronomers point their telescopes at distant galaxies, they don't just see pinpricks of light, they see cosmic fingerprints encoded in color. The light from these galaxies isn't just traveling through space, it's being stretched as space itself expands, shifting toward the red end of the spectrum like a cosmic rubber band. This phenomenon, called redshift, is one of the most crucial clues we have about the universe's expansion. Here's how it works. Every element in the universe, hydrogen, helium, oxygen, absorbs and emits light at specific wavelengths, creating unique patterns called spectral lines. Think of these like barcodes for the cosmos. When scientists analyze light from a galaxy, they expect to see these familiar patterns, but with distant galaxies, something bizarre happens. Those barcodes appear shifted toward longer, redder wavelengths. The farther the galaxy, the more extreme the shift. It's as if the universe itself is tugging on the light, leaving behind a telltale stain of redshift. The real magic happens when astronomers compare these stretched spectral lines to their known positions in a lab. Hydrogen on Earth, for example, emits light at a wavelength of 656 nanometers, a deep red. But that same hydrogen line in a galaxy billions of light-years away might appear at 700 nanometers or beyond. By measuring this shift, scientists can calculate exactly how fast that galaxy is racing away from us. The numbers are staggering. Some galaxies show redshift so extreme, their light has stretched nearly tenfold since it began its journey to our telescopes. This isn't just abstract math. Those redshift measurements have allowed us to reconstruct the universe's expansion history like chapters in a cosmic biography. When we observe a galaxy with a redshift of 1, we're seeing it as it was when the universe was half its current size. A redshift of 3, that's the universe at a quarter of its present size. Each increment peels back another layer of time, revealing how the expansion has accelerated over billions of years. What's truly mind-blowing is how this simple color shift connects to Einstein's equations. Redshift doesn't just tell us galaxies are moving. It proves space itself is stretching, carrying galaxies along for the ride. And the deeper we look, the more extreme the redshifts become, confirming Hubble's law with razor-sharp precision. The most distant galaxies we've observed have redshifts over 11, meaning their light has been stretched to more than 12 times its original wavelength. That's the universe showing its hand, revealing an expansion so relentless, it's rewriting the very laws we thought governed reality. In the vast darkness of space, some stars go out with a bang so bright and precise, they act like cosmic lighthouses flaring up with near-identical brilliance every single time. These are Type 1, a supernova, the universe's ultimate standard candles, and in 1998 they revealed a secret about cosmic expansion so shocking it would earn scientists a Nobel Prize. Here's how it works. When a dense white dwarf star siphons too much material from a companion, it crosses a critical mass threshold and detonates in a thermonuclear explosion so powerful it briefly outshines entire galaxies. But the real magic lies in the consistency, because these explosions always peak at the same intrinsic brightness. Astronomers can compare how bright they appear from Earth to calculate their distance with incredible precision. Two teams, the Supernova Cosmology Project and the High-Z Supernova Search, spent years scouring the skies for these stellar explosions in distant galaxies. By painstakingly measuring their light curves, the way their brightness fades over time, they could determine not just how far away they were, but how fast the universe was expanding when their light first erupted. The expectation was clear. Gravity should have been slowing the expansion, like a ball tossed upward, gradually losing speed, but the data told a different story. Supernova billions of light-years away were dimmer than they should have been, meaning they were farther off than anyone predicted. The universe wasn't just expanding, it was accelerating, as if some invisible force was pressing harder on the gas pedal over time. The implications were staggering. Imagine tossing that ball upward only to watch it rocket away faster instead of falling back. This wasn't just a tweak to existing models, it upended our entire understanding of cosmic dynamics. The team's graphs, plotting supernova distances against their redshifts, showed a curve bending upward, a smoking gun for acceleration. Overnight, dark energy went from a fringe hypothesis to the dominant force shaping the universe's fate. What makes this discovery even more remarkable is the sheer audacity of the method. These researchers were using dying stars as cosmic yardsticks, stitching together a narrative of expansion across billions of years. The most distant supernova they studied, labeled 1997 FF, erupted when the universe was just half its current age, yet its light told the same unnerving story. Even now, every new Type 1, a supernova detected, adds another day to point to this accelerating universe, a silent testament to the hidden force we're still struggling to comprehend. The Nobel Prize was just the beginning. The real revelation was that the cosmos is playing by rules we're only starting to decode. Right now, something is deeply wrong with our cosmic calculations, and it threatens to unravel decades of astrophysics. Picture two teams of scientists using completely different methods to measure the universe's expansion rate, each confident in their approach. One group studies the echoes of the Big Bang, peering back to the universe's infancy. The other observes pulsating stars and exploding supernova in our cosmic backyard. Both methods are meticulous, both have been tested for years, yet they keep arriving at stubbornly different answers. The early universe data suggests an expansion rate of 67 kilometers per second per megaparsec, while local measurements insist it's 73. That gap might seem small, but in the precision-driven world of cosmology, it's a glaring discrepancy known as the Hubble tension. Think of it like two clocks in the same room, each built by master craftsmen, ticking at slightly different speeds. One clock is calibrated using the universe's oldest light, the cosmic microwave background, a relic from 380,000 years after the Big Bang. The other clock is set by Cepheid variable stars, whose rhythmic brightening and dimming act like cosmic metronomes, and supernovae that erupt with predictable brilliance. These shouldn't disagree, yet they do. Graphs plotting their results don't overlap neatly. They form parallel lines separated by a chasm of uncertainty. So what's causing this rift? Some physicists are racing to propose exotic solutions. Could there be an unknown particle, a shadowy, dark radiation flooding the early cosmos? Might dark energy itself be evolving, growing stronger over time? Others wonder if we're missing something fundamental about gravity, a flaw in Einstein's equations that only becomes obvious across vast cosmic distances. More cautious voices argue for hidden measurement errors like cosmic dust dimming supernova or quirks in how we track Cepheid stars. The stakes couldn't be higher. If the tension persists, it could mean our standard model of cosmology, the very framework we use to understand the universe's birth, growth, and fate, is incomplete. Every new observation tightens the screws. The James Webb Space Telescope's razor-sharp infrared vision has ruled out some measurement errors, deepening the mystery. Meanwhile, independent techniques like tracking gravitational waves from colliding neutron stars are now entering the fray, offering a third way to measure expansion. This isn't just academic squabbling. The Hubble tension is a crack in the foundation of modern physics, and whether it's filled with new particles, tweaked theories, or revolutionary ideas, one thing is certain: the universe is hiding something. And when the dust settles, we may find ourselves staring at a cosmic rulebook rewritten. Imagine holding a photograph of the universe just 380,000 years old, a cosmic baby picture revealing its very first light. That's exactly what the Planck satellite delivered, a map of the cosmic microwave background, or CMB, the afterglow of the Big Bang itself. This faint microwave whisper blankets the entire sky, and etched into its subtle temperature variations are secrets about how fast the universe has been expanding for over 13 billion years. The CMB isn't just static, it's a fingerprint. Tiny fluctuations, regions slightly hotter or colder than average, form a pattern that's shockingly precise. Picture the surface of a lake on a windy day, covered in ripples of different sizes. Planck's instruments measured these ripples in exquisite detail, down to 1 part in 100,000. Why does that matter? Because the spacing between those hot and cold spots acts like a cosmic ruler. The physics of the early universe determined how far sound waves could travel before the CMB froze into place, leaving behind a preferred scale imprinted in the sky. When scientists analyze this pattern, they're essentially taking the universe's temperature, not just its heat but its expansion rate. The peaks and troughs in Planck's famous map correspond to oscillations in the primordial plasma, and their angular size on the sky tells us how much the universe has stretched since the light began its journey. It's like finding a stretched-out barcode. The amount it's deformed reveals how much space has expanded. Here's where things get even wilder. By combining the CMB data with our understanding of dark matter and dark energy, Planck pinned the universe's expansion rate, the Hubble constant, at 67 kilometers per second per megaparsec. That number isn't just plucked from thin air. It's the result of painstakingly matching theoretical models to the CMB's intricate speckles. But here's the twist. This early universe measurement clashes with modern observations of supernova and Cepheid stars, which suggest a faster expansion. The discrepancy isn't a small error, it's a full-blown cosmic mystery. What makes Planck's results so groundbreaking is their sheer precision. The satellite's detectors were chilled to near absolute zero to catch the faintest whispers of the CMB, mapping it in 9 frequency bands to filter out Milky Way interference. Those tiny temperature differences, some as minuscule as a millionth of a degree, encode the universe's composition. 5% ordinary matter, 27% dark matter and 68% dark energy. The CMB is more than a relic, it's a time capsule, and Planck's data has become the gold standard for testing theories about the universe's infancy, yet the plot thickens. The very same CMB patterns that constrain the Hubble constant also hint at something even stranger: anomalies. Large-scale features in the map, like the infamous cold spot, defy expectations. Could these be scars from a collision with another universe, or evidence that dark energy isn't constant after all? The answers might lie in the next generation of CMB experiments, already scanning the skies with even sharper eyes. For now, Planck's snapshot remains our clearest window into the primordial cosmos, a frozen moment whispering secrets we're still learning to decode. Think of the early universe as a simmering cosmic soup, a seething plasma of particles and light, where gravity and pressure battled in a rhythmic push and pull. When the first atoms formed and light broke free, these ripples froze in place, imprinting the cosmos with a hidden grid of sound waves. Billions of years later, we can still see their echo in the way galaxies cluster across the sky. These are Baryon acoustic oscillations, nature's own yardstick for measuring the universe's expansion. The Sloan Digital Sky Survey has turned this cosmic ruler into a tool of breathtaking precision. Imagine pointing a telescope at millions of galaxies, then plotting their positions in a vast three-dimensional map. Instead of randomness, you'd notice something uncanny: galaxies are slightly more likely to be separated by 500 million light-years, as if spaced by some invisible hand. That's the BAO signal, the fossilized imprint of those ancient sound waves, stretched by expansion but still detectable as a subtle overabundance of galaxy pairs at that specific scale. Here's how it works. In the universe's first few 100,000 years, gravity pulled matter inward while radiation pressure pushed it outward, creating oscillations like ripples in a pond. When light finally escaped, those ripples froze, leaving shells of matter at a fixed distance from each original density peak. Fast forward to today, and those shells have stretched with the expanding universe, but their relative spacing remains a benchmark. By measuring how much that standard distance appears stretched in our observations, astronomers can track how much the cosmos has grown. The Sloan Survey's galaxy maps reveal this pattern with stunning clarity. Peaks in the data correspond to those ancient sound wave signatures, visible as concentric rings in statistical analyses. It's as if the universe left behind a series of nested bubbles, each telling us how much space has expanded since the dawn of time. And the real power of BAO, unlike supernova or Cepheid stars, it doesn't rely on understanding a single object's brightness. It uses the large-scale structure of the universe itself as a calibration tool. What makes this even more remarkable is how BAO ties into other cosmic measurements. Combined with the cosmic microwave background, it forms a cross-check that's virtually immune to systematic errors. While Planck's CMB data gives us a snapshot of the infant universe, BAO reveals how that infant grew into the cosmic web we see today. Together, they've helped pin down the universe's composition and expansion rate with unprecedented precision. Yet they also deepen the Hubble tension, as their results stubbornly disagree with local measurements. The next generation of surveys, like the Dark Energy Spectroscopic Instrument, are mapping BAO with even finer resolution, spanning billions of galaxies across 10 billion light-years. These projects aren't just refining our ruler, they're probing whether dark energy's strength has changed over time, or if unknown physics altered the universe's growth. Every new data point peels back another layer, revealing how those primordial sound waves shaped everything from galaxy clusters to the voids between them. The echoes of the Big Bang aren't just a relic, they're an active tool, helping us measure the universe's pulse as it races into the unknown. It's humbling to realize that everything we see, every star, galaxy, and swirling nebula, makes up less than 5% of the universe's total content. The rest is an invisible realm ruled by two shadowy titans, dark matter and dark energy. But here's the twist that flips cosmic understanding on its head. Dark energy alone commands a staggering 68% of the universe's energy budget. Imagine a pie chart of the cosmos shortly after the Big Bang, a dense, hot mix of radiation, matter, and a whisper of dark energy hiding in the background. Fast forward 9 billion years and the balance shifts dramatically. Matter clumps into galaxies, but its influence wanes as the universe grows. Then, around 5 billion years ago, dark energy staged a silent takeover. Today's cosmic pie chart tells a story of utter dominance. Ordinary matter, the stuff of planets, trees, and human bodies, is a mere sliver. Dark matter, though invisible, makes up 27%, sculpting galaxies with its gravitational pull. But dark energy, it's the heavyweight, filling the void between galaxies and flexing its repulsive gravity like an unseen hand stretching space-time itself. This isn't just a subtle nudge, it's the reason distant galaxies now race away at speeds that defy logic. What's even stranger is how dark energy's influence grows as the universe expands. Picture a rubber sheet being stretched. The more it expands, the more dark energy seems to pour into the gaps, accelerating the process. If you rewind cosmic history, dark energy was barely a footnote. In the early universe, matter's gravity ruled, slowing expansion like a cosmic brake. But as galaxies drifted apart, dark energy's push overcame gravity's pull, turning the universe's fate into a high-speed escape with no end in sight. This flipping of the cosmic script raises spine-tingling questions. Is dark energy truly constant, or could it evolve over time? Some theories suggest it might grow stronger, eventually shredding galaxies, stars, and even atoms in a distant Big Rip. Others propose it could fade, allowing gravity to claw back control. For now, our best clues come from those pie charts, snapshots of a universe where the unseen reigns supreme, and the fate of everything hinges on a mystery we've only begun to unravel. One of the most unsettling possibilities lurking in our universe's future isn't just expansion, it's annihilation by stretching. Picture this: trillions of years from now, the relentless pull of dark energy grows so strong that it doesn't just push galaxies apart, it shreds them from the inside out. This is the Big Rip, an apocalyptic scenario where the fabric of spacetime itself becomes a cosmic executioner. The horror unfolds in stages. First, galaxy clusters, bound by gravity for billions of years, begin to drift apart as dark energy overpowers their attraction. The Virgo cluster, our local galactic neighborhood, dissolves like sugar in hot water. Next, individual galaxies unravel. The Milky Way's spiral arms stretch and snap, stars flinging into the void like beads from a broken necklace. Then gravity loses its grip entirely. Solar systems are torn apart, planets ripped from their suns with violent finality. Even stars themselves can't hold together. Their hydrogen atoms stretch beyond nuclear bonds, snuffing out their light forever. But the true nightmare comes in the final moments. Minutes before the end, dark energy's grip reaches down to the subatomic level. Electrons are wrenched from their orbits, protons and neutrons stretched until quarks snap apart. Reality itself disintegrates into a sea of unconnected particles, screaming into the void at speeds faster than light. The universe, once a vibrant tapestry of structure, becomes a featureless, cold expanse where not even atoms can exist. Timeline estimates vary, but calculations suggest this cosmic demolition could happen in as little as 22 billion years. That might sound distant, but on a cosmic scale, it's just a blink. Some models even propose that if dark energy's strength increases over time, a hypothetical called phantom energy, the rip could arrive much sooner, accelerating the countdown to oblivion. What makes this scenario especially chilling is how it inverts our understanding of destruction. Most cosmic doomsdays, like the Big Crunch or heat death, happen gradually. The Big Rip is violent, abrupt, and inescapable. There's no black hole to hide in, no distant corner of spacetime safe from stretching. every point in the universe would experience the same horrific unmaking simultaneously. Yet strangely, this terrifying idea is also a testament to science's power. The fact that we can take the equations of dark energy and extrapolate them to their logical extreme, even if it predicts an end so absolute, shows how deeply we've begun to understand the forces shaping our reality. The Big Rip might remain speculative, but it forces us to confront an undeniable truth. The universe plays by rules we're only beginning to decipher, and some of those rules might be far stranger than we ever imagined. Quantum physics and cosmology are supposed to fit together like pieces of a puzzle, but when it comes to vacuum energy, they're off by a number so absurdly huge, it's been called the worst prediction in the history of science. Picture this: the quantum fields that permeate every inch of space are constantly flickering with virtual particles popping in and out of existence. These fleeting fluctuations should generate a staggering amount of energy, enough to warp spacetime beyond recognition. Quantum field theory calculates this vacuum energy density by adding up all those microscopic contributions. But here's where the math goes off the rails. The theoretical value comes out to 10 to the power of 120 times larger than what we actually observe in the cosmos. To grasp just how enormous that discrepancy is, imagine filling the entire observable universe with sand, every star, galaxy, and empty void replaced by grains. Now imagine counting every single grain. That number wouldn't even come close to the magnitude of this mismatch. 10 to the 120 is a 1 followed by 120 zeros, so vast it defies analogy. If the quantum calculation were correct, the repulsive force of vacuum energy would have torn atoms apart before stars could even form, leaving the universe a featureless void. The fact that we exist at all suggests something is deeply wrong with our understanding. Cosmologists measure dark energy's density through painstaking observations, supernova redshifts, Baryon acoustic oscillations, the cosmic microwave background. These tools all point to a value so tiny it's practically zero when compared to quantum predictions. The frustration is palpable. Two of physics' most successful theories, quantum mechanics and general relativity, give answers that disagree by 120 orders of magnitude. It's like using two different GPS systems, one guiding you to a coffee shop down the street, the other sending you to a different galaxy. Some theorists argue the solution lies in undiscovered physics, a symmetry or cancellation mechanism that mysteriously nullifies most of vacuum energy's effects. Others propose dark energy isn't constant at all, but a dynamic field slowly decaying over cosmic time. Then there's the radical idea that we're seeing a selection effect. In a hypothetical multiverse, only regions with near-zero vacuum energy could host life, placing us in a lucky bubble where the numbers just barely allow galaxies to form. Whatever the answer, the vacuum energy paradox remains a glaring reminder of how much we don't understand. The equations scribbled in quantum physics textbooks and the data streaming from telescopes tell irreconcilable stories, and bridging that gap might require rewriting the rules of reality itself. For now, this monstrous discrepancy stands as both an embarrassment and an inspiration, proof that even our sharpest theories are still missing something fundamental about the fabric of the cosmos. If dark energy is unsettling, phantom energy is downright terrifying, a hypothetical version that doesn't just push the universe apart but grows stronger with time. Unlike ordinary dark energy, which remains constant as space expands, phantom energy intensifies, its repulsive gravity snowballing until it unravels reality itself. Picture a runaway train where the engine doesn't just maintain speed, it accelerates uncontrollably, tearing the tracks apart beneath it. That's phantom energy's effect on space-time, an ever-increasing force that could make the Big Rip inevitable. The math behind this scenario is chilling. Most dark energy models assume a cosmological constant, a steady pressure per unit of space. But phantom energy's equation of state, a critical parameter in cosmology, dips below -1, meaning its density actually increases as the universe expands. It's as if stretching spacetime somehow feeds the beast, creating a feedback loop of destruction. Simulations show that with phantom energy, galaxy clusters wouldn't just drift apart, they'd be yanked from each other with violent force, their gravitational bonds snapping like overcooked spaghetti. Even black holes, the universe's most indestructible objects, wouldn't be safe. Here's where it gets even stranger. If phantom energy exists, it could trigger the Big Rip not in some distant trillion-year future, but within a cosmologically short time frame. Some estimates suggest just tens of billions of years, a blink compared to the universe's current age. The final moments would be grotesquely theatrical. Stars ripped apart while still shining, planets torn from orbits mid-rotation, and atoms themselves stretched beyond recognition. Unlike the heat death scenario where the universe fades slowly into darkness, phantom energy promises a violent, cinematic end. Yet the most unsettling part isn't the destruction, it's the way phantom energy warps our understanding of physics. Most substances in the universe obey the null energy condition, a foundational rule that prevents certain impossible phenomena like time travel or perpetual motion machines. Phantom energy violates this condition so flagrantly that some physicists argue it can't exist without rewriting the laws of thermodynamics. Others counter that dark energy's true nature is still unknown, and phantom behavior might emerge from quantum fields we've yet to discover. Observational clues are sparse but tantalizing. The universe's acceleration appears consistent with a cosmological constant for now, but subtle deviations in supernova data, like slightly faster than expected expansion at certain redshifts, leave room for phantom energy to hide in the margins. Upcoming telescopes, like the European Space Agency's Euclid mission, are hunting for these anomalies, measuring cosmic expansion with precision sharp enough to spot phantom energy's fingerprints. The irony is delicious. Phantom energy's potential horror stems from the same equations that describe dark energy's mild-mannered acceleration. By tweaking just one parameter, cosmologists can flip the universe's fate from gradual expansion to apocalyptic shredding. Whether this scenario is real or just a mathematical nightmare, it forces us to confront how little we know about the force shaping our cosmic destiny. The universe might not just fade away, it could be torn apart by its own shadow. The cosmological constant may be the simplest explanation for dark energy, but what if it's not a constant at all? Enter quintessence, a dynamic dark energy model that breathes new life into the equation. Unlike Einstein's static cosmological constant, quintessence proposes a cosmic fluid that evolves over time, its strength waxing or waning as the universe expands. Picture a pendulum slowly losing momentum, except in this case, the pendulum's swing could determine whether the universe ends in a big rip or a graceful fade. At the heart of quintessence lies a hypothetical scalar field, a kind of invisible energy that permeates all of space. Think of it like an ocean whose tides subtly shift the cosmos's expansion rate. Unlike the flat, unchanging potential energy of the cosmological constant, quintessence fields have curves literally. Diagrams of their potentials often show graceful slopes or shallow bowls, illustrating how the field's energy density changes as it rolls toward equilibrium. Some models resemble a ball gently descending a hill, losing speed as it goes. Others feature abrupt drops where the field could suddenly thaw and trigger cosmic phase transitions. The brilliance of quintessence is how it dances between competing cosmic forces. Early in the universe's history, when matter was densely packed, this field might have lain dormant, its energy dwarfed by gravity's grip. But as galaxies drifted apart, the field could have awakened, its repulsive push growing just enough to explain today's accelerating expansion. Some versions even allow for oscillations, periods where dark energy's strength fluctuates, alternately speeding up and slowing down cosmic growth like a cosmic heartbeat. Observational clues could lurk in supernova data. If dark energy's strength has changed over billions of years, distant supernova might show subtle deviations from the cosmological constant's predictions. Imagine plotting their brightness against redshift and spotting a curve that isn't quite smooth, a hint that the universe's expansion pedal wasn't always pressed to the floor. The challenge: these variations would be tiny, buried in noise, and devilishly hard to confirm. Yet quintessence isn't just a theoretical toy. It offers elegant solutions to cosmology's thorniest puzzles. That infamous vacuum energy discrepancy, a rolling scalar field, could naturally cancel out most of quantum theory's absurdly large predictions, leaving behind the faint whisper we call dark energy. The Hubble tension, perhaps early quintessence activity, subtly altered the expansion rate, leaving today's measurements out of sync. The most tantalizing versions involve tracker fields, self-adjusting quintessence that locks on to the dominant energy of the era, whether radiation, matter, or dark energy. It's as if the universe has a built-in thermostat, fine-tuning its own expansion behind the scenes. Of course, for all its allure, quintessence remains unproven. Without direct detection of its hypothetical field, it's a ghost in the equation's beautiful math in search of physical proof. Future galaxy surveys and precision cosmology experiments may soon change that. By mapping the universe's expansion history with razor-sharp accuracy, scientists could spot the telltale fingerprints of a dynamic dark energy, distinguishing it from Einstein's static constant. Whether quintessence is real or just another cosmic mirage, its very existence as a possibility reminds us how much we still have to learn about the forces scripting the universe's fate. The universe didn't just start expanding. It exploded into existence with a growth spurt so violent, it makes today's acceleration look sluggish. In the first sliver of a second after the Big Bang, space underwent a dramatic phase called inflation, ballooning from smaller than an atom to the size of a grapefruit in less than a trillionth of a second. That's like stretching a single DNA strand to the length of the observable universe almost instantly. But here's where it gets weird. Inflation's breakneck expansion and today's dark energy-driven acceleration might be cosmic cousins, two bookends of the universe's story, separated by billions of years but linked by the same underlying physics. Inflation solved some of cosmology's biggest puzzles, like why the universe looks so smooth in every direction. By stretching space exponentially, it ironed out wrinkles, leaving behind the nearly uniform cosmic microwave background we see today. But that growth didn't just smooth things out, it also planted the seeds for all cosmic structure. Quantum fluctuations, magnified to cosmic scales, became the blueprints for galaxies. Now fast forward to the present. Dark energy is driving another expansion phase, but this time it's gradual and linear. Plot both events on a logarithmic timeline and the difference is stark. Inflation's vertical spike looks like a skyscraper next to the gentle slope of today's acceleration. Yet both share an eerie resemblance in how they stretch space-time itself. The critical distinction lies in their triggers. Inflation was likely powered by a hypothetical field called the inflaton, a relative of the Higgs boson that temporarily dominated the universe's energy density. When this field collapsed, its energy reheated the cosmos, birthing the particles we know today. Dark energy, by contrast, seems passive, a constant background hum that only gains dominance as matter dilutes over cosmic time. But some theorists speculate they might be two faces of the same phenomenon. Could dark energy be the faint afterglow of inflation, a low-energy remnant of that primordial fire? Or is the universe cycling between phases of rapid and slow expansion, like a cosmic lung inhaling and exhaling? Evidence for inflation comes from the CMB's telltale pattern, slight temperature variations that match predictions flawlessly. Dark energy's fingerprints, meanwhile, are stamped across supernova redshifts and galaxy surveys. Yet both remain mysteries, their fundamental natures hidden behind equations. The tantalizing possibility, understanding one might unlock the other. If inflation's field decayed into today's dark energy, we could be living in the tail end of a trillion-year cosmic process where the universe's first breath never truly ended, it just slowed to a whisper. Future gravitational wave detectors might uncover inflation's ripples, while dark energy surveys could reveal whether its strength is truly constant or decaying. Either way, these two epochs of expansion aren't just history, they're the framework holding reality together. What if the speed of light isn't constant but has been slowing down since the dawn of time? It sounds like a fringe idea, but a small group of physicists argue that a variable speed of light could explain cosmic acceleration without dark energy. Imagine rewinding the universe's tape. As light moves faster in the past, distant supernovae appear dimmer not because space is stretching, but because their light once traveled quicker, throwing off our distance calculations. This radical rewrite of Einstein's relativity could turn cosmology upside down, swapping dark energy's mysterious push for a simple change in light's speed limit. The most compelling version of this idea comes from bimetric gravity, a theory proposing two parallel spacetimes with their own metrics like twin fabrics interwoven but slightly out of sync. In one spacetime, light zips across galaxies at today's speed. In the other, it races faster, shaping how gravity propagates. Visualize it as two overlapping grids. Matter bends one grid while light speed depends on the other, creating an illusion of expansion when really, it's just a mismatch between how matter and light experience space. Side-by-side diagrams of these spacetimes show curved sheets deforming at different rates, with a gap between them mimicking Hubble's law. Critics pounce on a glaring issue. If light speed changed, the fine structure constant, a fundamental number governing atomic physics, should show wild variations. Yet quasar absorption lines reveal this constant hasn't budged in 12 billion years. Proponents counter with tweaked models where electromagnetism's constants shift in lockstep, preserving observed physics while letting light speed secretly evolve. It's a delicate dance of equations, but one that could explain why supernova data fits both accelerating expansion and variable light scenarios equally well. The real test may come from merging neutron stars. When these dense corpses collide, they blast gravitational waves and light simultaneously. By comparing their arrival times across billions of light years, we could catch light lagging behind if its speed truly changed. So far, LIGO detections side with Einstein, but future observations might reveal discrepancies hidden in the noise. Until then, variable light speed remains a tantalizing what if, reminding us that even the universe's most trusted constants might still hold surprises. Zoom out from our Milky Way past neighboring galaxies, and you'll notice something bizarre. The cosmos around us isn't just expanding, it's lopsided. We might be floating inside one of the universe's largest known structures, the KBC void, a gargantuan bubble of relative emptiness spanning over 2 billion light-years. Imagine living in a cosmic Swiss cheese hole where galaxies are sparser than the surrounding universe. This isn't just a curiosity. It could throw off our measurements of cosmic expansion in ways we're only beginning to understand. Galaxy surveys paint a striking picture. Most of the universe resembles a dense web with galaxies clustered along shimmering filaments. But when astronomers like Amy Barger and her team mapped our local region, they found a startling underdensity, a pocket where matter is 20% scarcer than the cosmic average. Slice through 3D maps from projects like the Sloan Digital Sky Survey, and the void pops like a blister in the cosmic fabric. Surrounding us on all sides, it's as if we're trapped in a clearing while the rest of the universe parties in a crowded forest. Why does this matter for measuring expansion? Hubble's law assumes a uniform universe, but gravity's pull varies with density. Inside a void, the lack of surrounding mass means galaxies drift away slightly faster than they would in a denser region. It's like being on a trampoline with fewer people. Your side stretches more easily. Recent calculations suggest this could skew our local Hubble constant measurements by up to 2.4 kilometers per second per megaparsec, just enough to nudge the needle toward the higher values fueling the Hubble tension. The controversy lies in proving it. Some simulations show voids this large are statistically unlikely in standard cosmology, like rolling a die 100 times and never landing on 6. Others argue we're seeing a rare but possible fluctuation. Future galaxy surveys, like those from the Vera Rubin Observatory, will test this by counting millions of galaxies to see if our neighborhood truly stands out. Until then, the KBC void remains a tantalizing reminder. When measuring the universe, your vantage point might be the ultimate wild card. Could dark energy be growing stronger or weaker over billions of years? The answer might lie in ghostly whispers from supernova that exploded when the universe was half its current age. Imagine cosmic detectives comparing those ancient explosions to modern ones, searching for subtle differences in how fast space was expanding then versus now. That's precisely what astronomers are doing, and the evidence is turning up some startling possibilities. Take supernova 1997 FF, one of the most distant stellar explosions ever observed. Its light spent nearly 10 billion years traveling to us, acting as a time capsule from an era when dark energy's grip was weaker. By measuring how much its light stretched its redshift and comparing its brightness to local supernova, scientists can reconstruct the universe's expansion history like tree rings. Plotting hundreds of these cosmic beacons across time reveals a curve. If dark energy were constant, the line would follow a smooth arc, but some datasets show slight kinks, hinting that dark energy's push might have fluctuated. The real test comes when combining supernova data with Baryon acoustic oscillations, those frozen sound waves from the early universe. BAO measurements act like cosmic mile markers, revealing how much space stretched between galaxies at specific epochs. When paired with supernova, they paint a three-dimensional picture of expansion. Recent analyses show intriguing tensions. Some redshift ranges suggest slightly faster acceleration in the past, while others align with today's rate. It's as if dark energy took its foot off the pedal briefly, then pressed down harder. One leading theory suggests dark energy could be a field slowly decaying, like a battery losing charge over cosmic time. Mathematical models show its strength dropping by mere percentiles over billions of years, enough to tweak expansion rates but not enough to erase its dominance. Other simulations propose the opposite. Dark energy might grow denser as space expands, amplifying its repulsive effects in a feedback loop. The uncertainty stems from how finely we can measure these ancient signals. Current telescopes like the James Webb are pushing the limits, capturing supernova so distant their light reveals epochs when dark energy was just beginning to overtake gravity. What makes this detective work so challenging is the sheer subtlety of the clues. A 1% change in dark energy's strength over 10 billion years translates to microscopic shifts in supernova brightness, differences easily drowned out by cosmic dust or calibration errors. Yet the payoff could rewrite cosmology. If dark energy varies, it might explain the Hubble tension, hint at connections to inflation, or even preview a future where acceleration suddenly stops. For now, every flicker of light from these dying stars carries a coded message, one we're still learning to decipher. What if dark energy isn't real, but a cosmic mirage created by our incomplete understanding of gravity itself? A growing chorus of physicists is exploring radical alternatives, rewriting Einstein's equations to explain the universe's acceleration without invoking mysterious dark energy. At the forefront is F of R gravity, a theory where spacetime curvature doesn't obey general relativity's rules at cosmic scales. Picture a rubber sheet that stiffens when stretched too far. Instead of dark energy pushing galaxies apart, space itself resists bending in unexpected ways, creating the illusion of an accelerating expansion. The key lies in that cryptic f of r symbol, a mathematical function that tweaks how spacetime responds to matter. In Einstein's original equations, the relationship between curvature r and gravity is linear, like a spring that stretches predictably. But f of r theories introduce nonlinear terms, as if the spring suddenly stiffens or softens depending on how much you pull it. Visualize spacetime as a trampoline. Place a bowling ball in the center, and it sinks predictably under general relativity. But under f of r gravity, the trampoline's fabric might ripple differently at the edges, subtly altering how distant objects appear to move. These modified gravity models shine brightest where dark energy stumbles. Take the Hubble tension, the nagging discrepancy between early and late universe expansion rates. F of r gravity can naturally produce faster expansion today without contradicting the cosmic microwave background, as if the universe's gravity settings were dialed differently across cosmic epochs. Some versions even mimic dark energy's effects so precisely, they're virtually indistinguishable in supernova data until you peer at the fine print, the catch. These theories demand extreme environments to reveal their quirks. Near black holes or in the early universe's chaos, f of r gravity predicts wild spacetime contortions, like ghostly extra-gravitational waves or lensing effects around galaxy clusters that Hubble should have spotted. So far, observations haven't caught these anomalies red-handed, but next-generation telescopes like LISA could change that. The irony is delicious. We might be chasing dark energy's shadow while the real answer hides in plain sight, etched into the geometry of spacetime itself. Whether f of r gravity survives scrutiny or collapses under data's weight, it forces us to confront an unnerving possibility that our cosmic maps might be missing entire dimensions of gravity's true nature. Neutrinos are the universe's most elusive escape artists. Billions pass through your body every second, leaving no trace. But these ghostly particles, once thought to be massless, now take center stage in one of cosmology's quietest revolutions. We've discovered they have mass, however tiny, and that slight heaviness shapes the cosmos in ways simulations make shockingly visible. Picture the cosmic web, that vast network of galaxies threaded along invisible filaments of dark matter. Now run two simulations side by side, one where neutrinos zip through space untouched, the other where their minuscule mass slows them just enough to alter gravity's grand design. The differences are subtle but profound, like comparing two spider webs where one has threads slightly rearranged. The numbers behind this are staggering. Even with masses millions of times lighter than electrons, neutrinos are so abundant their collective gravity nudges cosmic evolution. Their high speeds approaching light mean they smear out small-scale structures, acting like cosmic sandpaper on the universe's finer details. Zoom into simulations of galaxy clusters and you'll spot the neutrino effect. Fewer dwarf galaxies orbiting giants, voids between filaments slightly enlarged. It's as if someone erased every 10th building in a city skyline, leaving gaps where matter couldn't clump tightly enough. This isn't just theoretical. The Planck satellite's cosmic microwave background maps reveal telltale suppression in temperature fluctuations at certain scales, precisely the fingerprints massive neutrinos would leave. When combined with galaxy surveys like DAISY, the data suggests neutrinos contribute about 0.1% of the universe's total mass energy. That might sound negligible, but in the razor-edge balance between expansion and gravity, even this whisper of weight matters. The real twist, neutrinos might be throwing off our dark energy measurements. Their ability to smooth out small-scale structure affects how we calculate matter density, which in turn influences our estimates of dark energy's strength. Some theorists argue that properly accounting for neutrino masses could shrink, though not erase the Hubble tension. It's a reminder that the universe's grand narrative isn't written by dark energy and matter alone, but by countless subtle actors, each tweaking the story in ways we're only beginning to read. What makes this even wilder is how recently we confirmed neutrinos had mass at all. For decades, physics insisted they were weightless until underground detectors like supernovae and caught them oscillating between flavors, a quantum party trick only possible with mass. Now we know they're at least 6 million times lighter than electrons, but their exact weight remains unknown. Future experiments like Dune aim to pin it down, potentially cracking open new chapters in both particle physics and cosmology. Until then, every simulation reminds us, even the universe's faintest players leave shadows on the largest scales. Here's a cosmic puzzle that keeps astronomers awake at night. What if the universe is younger than some of the stars it contains? At first glance, that sounds impossible. How could the container be younger than its contents? Yet this strange contradiction emerges when we compare two of cosmology's most trusted measuring sticks, the ages of ancient star clusters and the universe's calculated age based on its expansion. The numbers don't quite add up, and the culprit might be dark energy's relentless acceleration. Let's start with the universe's official age, 13.8 billion years, a number etched into textbooks and derived from the cosmic microwave background. Planck satellite data, combined with our understanding of dark energy and matter, points to this figure with remarkable precision. But then we turn our telescopes toward globular clusters, dense swarms of stars orbiting the Milky Way's outskirts. These celestial fossils contain stars so ancient, their ages estimated by nuclear chemistry and stellar evolution models creep uncomfortably close to 14 billion years. Some, like HD 140283, nicknamed the Methuselah star, initially appeared to be over 14 billion years old, though later adjustments brought it just under the cosmic limit. The tension arises from how we measure these ages. Globular cluster stars act like cosmic clocks, their lifespans determined by how quickly they burn hydrogen. Low-mass stars, dim and cool, can chug along for longer than the universe's current age if their fuel consumption is slow enough. But when Hubble's law suggests a younger universe, especially if dark energy's acceleration has been stronger in the past, it creates a paradox. A faster expanding universe would have taken less time to reach its current size, potentially shaving hundreds of millions of years off its birthday. Astronomers have proposed fixes, from tweaking stellar models to re-evaluating globular cluster distances. Some suggest these clusters might be slightly closer than we thought, making their stars appear brighter and younger than they truly are. Others speculate that early dark energy, a brief surge of repulsive gravity in the universe's first few 100 million years, could have sped up expansion just enough to reconcile the timelines. The most radical solutions flirt with revising fundamental physics, like altering how stars fuse hydrogen or questioning the cosmological principle itself. What makes this dilemma so fascinating is how it exposes the fragility of our cosmic measuring tools. Both stellar ages and universal expansion rely on layers of assumptions, each a house of cards that could wobble if one underlying constant proves variable. The James Webb Space Telescope is now scrutinizing these ancient stars with unprecedented clarity, hunting for subtle chemical signatures that might reset their clocks. Meanwhile, next-generation CMB experiments could reveal whether dark energy's early behavior was weirder than we imagined. Until then, the cosmic age problem stands as a humbling reminder. Even our best estimates of the universe's timeline might still be missing a page or two. The answers could rewrite not just textbooks, but our understanding of how stars and space itself grow old together. The next chapter in our quest to unravel dark energy's secrets lies not just in theories, but in towering technological marvels now taking shape on Earth and beyond. NASA's Nancy Grace Roman Space Telescope, set to launch by 2027, isn't your average observatory. It's a dark energy detective armed with a mirror 2.4 meters wide and a field of view 100 times larger than Hubble's. Picture a camera that can capture the equivalent of 100 full moons in a single snap, surveying thousands of supernovae and millions of galaxies in its 6-year mission. But Roman's real power lies in its high-latitude survey, a sweeping scan of the cosmos designed to measure Baryon acoustic oscillations and weak gravitational lensing with razor-sharp precision. These subtle distortions in space-time caused by dark matter's invisible hand will trace how dark energy's push has evolved across cosmic epochs like fingerprints on a cosmic crime scene. Meanwhile, the European Space Agency's Euclid telescope is already pioneering this frontier from its perch at Lagrange Point 2, a gravitational sweet spot 1.5 million kilometers from Earth. Euclid's infrared eyes and optical sensors are mapping 1/3 of the sky, measuring galaxy shapes and redshifts to reconstruct dark energy's influence with a technique called cosmic shear. Imagine holding a clear plastic ruler underwater. The way light bends as it passes through reveals hidden currents. Euclid does this on a galactic scale, detecting how dark energy warps the paths of light from distant galaxies as it stretches the universe. Early data releases hint at unprecedented 3-dimensional maps, revealing voids and filaments in the cosmic web with stunning clarity. But the revolution doesn't stop there. The Vera Rubin Observatory's legacy survey of space and time will soon unleash an avalanche of data, scanning the entire southern sky every few nights with a 3.2 gigapixel camera, the largest ever built. Its time-lapse view of the cosmos will catch supernova in the act, while tracking how galaxy clusters morph over years, offering real-time clues to expansion's acceleration. These missions share a common thread. They're not just hunting dark energy, but testing whether it's truly constant, or if its strength fluctuates like a cosmic heartbeat. The most tantalizing possibility: these telescopes might catch dark energy in the act of changing. If Roman or Euclid spot variations in the universe's expansion rate that don't fit the standard model, it could mean dark energy is evolving, perhaps decaying into other particles or interacting with dark matter in ways we've never imagined. The data could even reveal if our cosmic void, the KBC supervoid, is skewing measurements on a grand scale. As these observatories come online, they're not just tools, they're time machines. By combining their findings, we'll stitch together a continuous film of cosmic expansion, from inflation's first frantic moments to dark energy's current reign. The resulting maps won't just fill textbooks, they might force us to rewrite them, uncovering hidden chapters in the universe's biography that have been waiting billions of years to be read. Picture a boiling pot of water bubbles forming, expanding, and sometimes colliding as steam rises. Now imagine that on a cosmic scale, where each bubble isn't just foam but an entire universe, inflating at its own pace with its own physics. This is the mind-bending landscape of eternal inflation, a theory where our universe might be just one accidental bubble in an infinite froth of cosmic creation. According to this idea, the Big Bang wasn't a one-time event. It was a local eruption in a far vaster, eternal multiverse where space-time constantly births new realities like bubbles in champagne. What's truly wild is how these bubble universes could each have radically different expansion rates. Some might inflate so rapidly they tear themselves apart in a split second, while others could grow sluggishly, collapsing back into the cosmic foam before stars ever form. Ours, it seems, landed in a Goldilocks zone, expanding fast enough to avoid immediate collapse but slow enough for galaxies to take shape. Diagrams of this cosmic foam resemble a fractal sponge with bubbles nested within bubbles, each hosting its own version of physics. Some might have stronger dark energy, causing runaway acceleration, while others could lack it entirely, doomed to recollapse in a big crunch. The mechanism behind this stems from quantum fluctuations in the inflattened field, the same phantom-like energy that drove our universe's initial exponential growth. In regions where this field lingers at high energy, inflation keeps raging, spawning new bubbles endlessly. but where it decays, as it did in our pocket of reality, inflation stops, leaving behind a stable universe like a cooled patch of glass in molten lava. Simulations of eternal inflation show tendrils of false vacuum energy snaking through the multiverse, birthing bubble universes like buds on a cosmic vine. Here's where it gets even stranger. If two bubble universes collide, the impact could leave scars in the cosmic microwave background, ring like patterns of temperature variations where the shockwaves reverberated. Astronomers have searched for these bruises in Planck satellite data, with one candidate, the so-called cold spot, sparking furious debate. Could it be a bruise from a long-ago collision with another universe, or just a statistical fluke in the primordial soup? Either way, the mere possibility reshapes how we think about our universe's expansion. It might not be an isolated event, but one ripple in an ocean of cosmic inflation without end. The implications are staggering. If eternal inflation is real, then dark energy's acceleration in our universe might not be a fundamental law, just a local quirk of our bubble's physics. Somewhere out there in the foam, other universes could be experiencing contraction, stagnation, or expansion rates that make ours seem glacial. This isn't just science fiction. It's a frontier where string theory, quantum gravity, and cosmology collide, offering testable predictions. Future telescopes probing the CMB's finest details or gravitational wave detectors catching echoes of primordial collisions might one day find hard evidence that our universe is just one room in an infinite cosmic hotel, each with its own rules and its own fate. What if the universe's expansion isn't driven by dark energy at all, but by something as mundane as thermodynamics? Dutch physicist Erik Verlaine turned cosmology on its head with entropic gravity, a radical theory that treats gravity not as a fundamental force, but as an emergent effect of entropy, the universe's relentless tendency toward disorder. Picture a cosmic game of telephone, where gravity isn't a real force but an illusion created by the way information gets scrambled at the edges of space. At the heart of this idea is a stunning reversal. Instead of matter warping space-time, it's the flow of microscopic information that generates the effects we call gravity, and by extension, the universe's accelerating expansion. Here's how it works in practice. Imagine zooming in on the fabric of space-time until you reach the Planck scale, where reality itself becomes pixelated. Every bit of space holds quantum bits, tiny units of information, like a cosmic hard drive storing the universe's data. Now, when matter enters this pixelated grid, it disrupts the arrangement of these bits, creating what Verlaine calls elasticity in space-time. This disturbance generates an entropic force, much like how heat naturally flows from hot to cold. But here's the twist: at cosmic scales, this effect mimics gravity, pulling galaxies together, or when accounting for dark energy's acceleration, pushing them apart. The real magic happens when you apply this to cosmic expansion. In Verlaine's framework, the vacuum of space isn't empty, it's teeming with microscopic degrees of freedom, like an invisible foam of quantum information. As the universe expands, new space forms, adding fresh pixels to the grid. But these new pixels come with their own entropy, like unwritten memory cards appearing out of thin air. This influx of information creates an entropic pressure, pushing galaxies apart as the system naturally seeks equilibrium. The astonishing implication: dark energy's acceleration might just be spacetime's way of balancing its cosmic books, an emergent effect, not a mysterious substance. Critics argue entropic gravity struggles to match precision measurements like those from the Planck satellite or supernova surveys. Yet Verlaine's models produce graphs eerily similar to standard dark energy predictions, with one crucial difference: no exotic energy is needed. Instead of invoking a cosmological constant, his equations derive cosmic acceleration from first principles, the same thermodynamics that explains why ice melts or perfume disperses in a room. It's as if the universe runs not on gravity's pull, but on the same statistical rules that govern steam engines and black holes. The debate is far from settled, but entropic gravity forces us to confront a profound question. Do we live in a universe where the fundamental forces are written in stone, or one where even gravity is just a side effect of deeper informational physics? Future experiments like gravitational wave detectors sensitive to quantum spacetime fluctuations might tip the scales. Either way, Verland's theory reminds us that sometimes the most revolutionary answers don't come from adding new layers of mystery, but from realizing the truth was hiding in plain sight all along. Ever feel like reality might be nothing more than an elaborate projection, like the universe is just a flat, two-dimensional surface encoded with all the information needed to create our three-dimensional world? That's the essence of the holographic principle, a radical idea in theoretical physics that could reshape how we understand cosmic expansion. Picture this: just as a hologram stores a 3D image on a 2D film, the entire universe, its galaxies, its dark energy, even you watching this, might be nothing more than data etched onto some distant cosmic boundary. And the key to unlocking this mind-bending idea lies in a mathematical playground called AD/CFT correspondence, where gravity in one dimension emerges from quantum physics in another. Visualizing AD/CFT is like imagining a cosmic Russian nesting doll. On one side, you have an anti-de Sitter space, a warped, hyperbolic universe where gravity obeys Einstein's equations. On the other, a conformal field theory, a quantum system buzzing with particles but no gravity at all. The magic happens when these two seemingly unrelated worlds turn out to describe the same physics, just in different languages. It's as if the 3D universe we experience is just a shadow cast by quantum interactions happening on a 2D surface at its edge. Diagrams of this duality often show a funnel-shaped anti-de Sitter space, with its boundary acting like a holographic screen where all the universe's information is stored pixel by pixel. What does this have to do with cosmic acceleration? Dark energy's relentless push could be a side effect of how information gets processed on this cosmic hard drive. If spacetime itself emerges from quantum entanglement, those invisible threads linking particles across vast distances, then the universe's expansion might be less about mysterious energy and more about how the hologram updates its pixels. Some models suggest that dark energy's strength is tied to the way entanglement entropy scales with the universe's growth, as if the cosmos is constantly recalculating its own surface area to volume ratio. The implications are staggering. If the holographic principle holds, then the vacuum energy catastrophe, that infamous 120 orders of magnitude mismatch, could vanish overnight. In a holographic universe, vacuum energy isn't a physical substance filling space. It's a computational artifact, a byproduct of how the cosmic code renders reality. Even the Hubble tension might find resolution here, with discrepancies arising from how different observational methods sample the universe's underlying data structure. Yet for all its elegance, the holographic principle remains fiercely debated. Critics point out that our universe resembles de Sitter space, a cosmos dominated by dark energy, far more than the anti-de Sitter space where AD/CFT shines. But newer theories like DS/CFT are adapting the framework, suggesting our accelerating universe might still be a hologram, just one with different encoding rules. Whether this paradigm survives future tests or not, it forces us to confront a profound possibility that the universe's expansion isn't just something happening in space and time, but to space and time, as if reality itself is recoding its own operating system. Ever wonder what empty space looks like if you could zoom in past atoms, past subatomic particles, down to the very fabric of reality itself? You'd find something stranger than fiction, a seething quantum foam where spacetime itself churns like a stormy ocean. At scales 100 billion times smaller than an atom, particles and energy flicker in and out of existence so fast they barely break the rules of physics before vanishing again. These quantum fluctuations aren't just theoretical curiosities, they might be the invisible engine powering the universe's expansion, a microscopic frenzy with cosmic consequences. Visualize it like this. Imagine spacetime as the surface of a boiling pot of water. Bubbles constantly form and pop, each bubble a temporary distortion in the fabric of reality. Some theories suggest these fleeting fluctuations, virtual particles dancing in and out of existence, could exert a net outward pressure stretching spacetime itself. It's as if the universe is built on a foundation of endless tiny tremors, each one nudging galaxies farther apart like a cosmic drumbeat too subtle for our instruments to detect. The math behind this is staggering. Quantum field theory predicts that even in a perfect vacuum, space crackles with an energy density of 10 to the power of 113 joules per cubic meter, a number so vast it dwarfs the observed dark energy density by over 100 orders of magnitude. This is the infamous vacuum catastrophe, where theory and observation collide with absurd disagreement. But some physicists speculate that this quantum foam's behavior might change at cosmic scales, its frenetic activity averaging out to the gentle repulsion we call dark energy. Here's where the real magic happens. Certain models, like those involving the Casimir effect, show that restricting quantum fluctuations between two plates creates a measurable force, proof that these ephemeral particles can influence reality. Scale this idea up, and the universe itself might act like a cosmic Casimir cavity, with quantum foam in the vast voids between galaxies pushing outward while matter-rich regions resist, creating an imbalance that drives acceleration. The problem: we still don't know how to reconcile quantum mechanics' frenzied microscopic world with general relativity's smooth cosmic spacetime. Loop quantum gravity and string theory offer competing visions. Some depict spacetime as a network of woven threads, others as a holographic projection. But all agree on one thing: at the Planck scale, reality is anything but static. Future experiments, like ultra-precise measurements of gravitational waves or tabletop quantum gravity probes, might finally catch these fluctuations in the act, revealing whether the universe's expansion is written in the foam. What's truly mind-bending is the possibility that dark energy isn't some exotic substance, but simply spacetime's restless quantum nature writ large, an emergent property of the universe's smallest scales echoing across its grandest vistas. Until we can peer deeper into the quantum abyss, this idea remains a tantalizing maybe, a whisper from the void that might one day rewrite our understanding of everything. What if the universe isn't on a one-way journey toward endless expansion, but caught in an endless cycle of birth, death, and rebirth? Cyclic cosmology dares to imagine a cosmos without beginning or end, where each Big Bang is just the latest chapter in an infinite loop of creation. Picture a cosmic accordion expanding violently before collapsing back in on itself, only to explode outward once more. At the heart of this idea lies a stunning reimagining of spacetime itself, where the universe's expansion isn't the opening act, but merely the midpoint of an eternal dance. Roger Penrose's conformal cyclic cosmology paints this cycle in mesmerizing detail. His diagrams, elegant geometric sketches resembling hourglasses made of light, show universes called eons stretching and compressing across unimaginable timescales. Each eon begins with its own Big Bang, expands until all matter evaporates into radiation, then stretches so thin that its geometry becomes indistinguishable from the next eon's birth. It's as if the universe hits a cosmic reset button when it reaches maximum emptiness, repurposing its own fading echoes into the seeds of a new explosion. The brilliance of Penrose's model is how it sidesteps the need for singularities, those infinitely dense points where physics breaks down. Instead of a Big Bang emerging from nothing, his conformal mapping shows how an old eon's infinitely stretched spacetime seamlessly becomes the new eon's infinitely compressed starting point. Visualize it like a vinyl record played at the wrong speed. As one song fades into silence, the needle lifts and drops again, replaying the same album with fresh intensity. But how could evidence of past eons survive such annihilation? Penrose points to mysterious Hawking points in the cosmic microwave background, circular patterns of polarized light where supermassive black holes from a previous eon might have evaporated, imprinting their final screams onto the next cycle's dawn. These faint rings, some spanning dozens of degrees in the sky, could be cosmic fossils, ghostly signatures of an earlier universe's death throes. Skeptics argue these patterns might just be statistical flukes, but if confirmed, they'd rewrite cosmology's rulebook. The implications ripple through every aspect of cosmic expansion. In cyclic models, dark energy isn't a mysterious constant. It's a temporary phase, a cosmic lubricant easing the transition between contraction and rebirth. Some versions even suggest the strength of dark energy oscillates with each cycle, stronger in some eons and weaker in others. It's a radical departure from the standard narrative, where acceleration leads only to cold oblivion. Here, expansion is just prelude to renewal, yet cyclic cosmology faces formidable challenges. How does a universe devoid of particles remember enough information to birth a new one with similar physical laws? Why haven't we detected gravitational echoes from previous bounces in spacetime's fabric? And perhaps most puzzling, if the cycles are truly eternal, why isn't entropy, the universe's tendency toward disorder, infinitely high already? Penrose counters that black hole evaporation resets entropy at each transition, but the debate rages on. What makes this idea so compelling isn't just its audacity, it's how it recontextualizes everything we see. The galaxies racing away from us aren't fleeing toward nothingness, but perhaps toward a future collapse that births new stars, new planets, new chances for life. Even dark energy's push might be less about destiny than rhythm, one movement in a symphony without end. Whether cyclic cosmology survives future tests or fades into history, it reminds us that the universe's story might be far stranger and far grander than we've dared to dream. What if the very laws of physics aren't constant, but subtly shifting over billions of years? Some scientists speculate that tiny changes in nature's fundamental numbers, like the fine structure constant, could hold the key to cosmic expansion's mysteries. This constant, represented by the Greek letter alpha, governs how tightly electrons cling to atoms and how strongly light interacts with matter. If alpha were slightly different in the past, it could alter how atoms emit and absorb light across the cosmos, potentially mimicking dark energy's effects without invoking any mysterious force. The hunt for variations in alpha takes us to the farthest reaches of the observable universe. Quasars, those brilliant beacons powered by supermassive black holes, act as cosmic backlights. As their light journeys through interstellar clouds, specific elements like iron or magnesium absorb certain wavelengths, leaving dark lines in the quasar's spectrum. These absorption lines are nature's barcodes, their positions locked in place by alpha's value. By comparing these lines in distant quasars to those measured in labs on Earth, astronomers can check if alpha has drifted over cosmic time. Teams using the Keck and Very Large telescopes have analyzed hundreds of these systems, spanning billions of years. Their results are mind-bending. Some datasets suggest alpha might have been a few parts in a million smaller 10 billion years ago, as if the universe's quantum rulebook had a different fine print. If confirmed, even this minuscule change could cascade across physics. Atomic transitions would shift slightly, altering how stars burn and how light redshifts through space. Over cosmic distances, these effects might masquerade as accelerated expansion, fooling us into thinking dark energy exists when we're really seeing the ghost of evolving constants. Yet the debate is fierce. Other studies, like those from the European Southern Observatories, use spectrograph, find no evidence for alpha's variation. The discrepancies could stem from subtle calibration errors, temperature fluctuations in telescope instruments, or unknown interstellar physics muddying the signals. But the tantalizing possibility remains. What we call dark energy might be the universe's way of revealing that its deepest laws aren't as immutable as we thought. The implications ripple far beyond cosmology. If constants evolve, it challenges Einstein's equivalence principle, the bedrock of general relativity. Quantum fields might interact differently over time, or extra dimensions predicted by string theory could slowly unfurl, tweaking nature's numbers. Future telescopes like the Extremely Large Telescope will test these ideas with unprecedented precision, hunting for variations not just in alpha but in the proton-to-electron mass ratio too. Until then, the quasar absorption lines whisper a provocative question. Are we measuring the universe's expansion or its slow rewriting of its own rules? Buried beneath the cosmic microwave background's glow lies an even fainter whisper from the dawn of time, the cosmic neutrino background. These ghostly particles, born just 1 second after the Big Bang, have been streaming through space undetected for 13.8 billion years, carrying secrets about the universe's expansion that no telescope has ever captured. Imagine trying to photograph a snowflake in a blizzard using a camera made of fog. That's the scale of challenge physicists face in hunting these relics. Unlike the CMB's microwaves, which we can map with exquisite precision, neutrinos barely interact with matter at all, passing through entire planets like they're not even there. Yet their potential to rewrite cosmic history is staggering. When these neutrinos first decoupled from the primordial plasma, the universe was a seething hot soup about 10 billion degrees Celsius. As space expanded, their wavelength stretched just like the CMB's photons, but with a crucial difference. Neutrinos, being nearly massless at the time, raced away at almost light speed. This means their distribution across the sky could reveal how fast the universe was growing during those critical first moments when dark energy seeds were planted. Current models suggest the cosmic neutrino background should have cooled to just 1.95 Kelvin by now, colder than the CMB's 2.73 Kelvin, but no less rich in information. Detecting them would be like finding the universe's first fingerprint. While the CMB shows us a snapshot from 380,000 years after the Big Bang, neutrinos offer a glimpse a million times earlier. Their subtle gravitational influence slightly warped the CMB's patterns, creating faint signatures in the microwave background's polarization maps, spiral-shaped swirls called B-modes that next-generation telescopes like the Simons Observatory are hunting. Other proposals involve ridiculously sensitive detectors using ultra-cold materials like solid argon or superfluid helium, waiting years for a single neutrino from the dawn of time to bump into an atomic nucleus. The payoff: these ghosts could break the Hubble tension wide open. If early universe neutrinos carried more energy than predicted, they would have subtly altered the expansion rate during those first critical seconds, potentially reconciling the Planck satellite's measurements with today's supernova observations. Alternatively, their detected abundance might reveal unknown particle interactions that tweaked dark energy's emergence. Either way, capturing this signal would be like adding sound to the CMB's silent movie, transforming our flat images of cosmic dawn into a dynamic, evolving picture of creation itself. What makes this search so poetic is its inversion of scale. To understand the universe's grandest structures, galaxy clusters, dark energy's push, the cosmic web, we must master the art of sensing the most elusive particles imaginable. It's a reminder that the cosmos writes its history in multiple languages, and we're only just learning to decipher the faintest of them all. If wormholes, those hypothetical tunnels through space-time, actually exist, could they be silently warping our measurements of cosmic expansion? Picture the universe like a vast, expanding balloon with galaxies stuck to its surface. Now imagine poking two holes in that balloon and connecting them with a tube. That tube is a wormhole, a shortcut where space folds back on itself. Embedding diagrams of such wormholes show spacetime as a curved sheet, pinched like an hourglass, with the wormhole throat acting as a bridge between distant regions. If these structures are real, light traveling through them could arrive sooner than expected, making certain galaxies appear closer or farther than they truly are in the normal fabric of space. This isn't just science fiction. Einstein's equations allow for wormholes, though they'd require exotic matter with negative energy to hold them open. But here's the twist. If even one stable, traversable wormhole exists, it could skew our cosmic yardsticks. Supernova whose light took a wormhole detour might seem dimmer or brighter than standard models predict, throwing off calculations of the Hubble constant. It's like trying to measure a straight highway while secretly some cars are taking underground tunnels. Your speed estimates would be completely off. Visualizing this gets even stranger. In embedding diagrams, a wormhole's throat warps spacetime so severely that two distant points nearly touch. A light beam passing through the wormhole would follow a shorter path than one traveling through ordinary space, creating a mismatch in cosmic distance measurements. Some theorists suggest this could mimic the effects of dark energy, tricking us into thinking the universe is accelerating when it's really light taking cosmic shortcuts. The real challenge, wormholes, if they exist, would likely be rare and unstable. But even a handful scattered across the cosmos could subtly bias our datasets, especially if they preferentially connect dense regions like galaxy clusters. Upcoming gravitational wave detectors might spot their signatures, unusual echoes in the ripples of spacetime from colliding black holes, or patterns in the cosmic microwave background that hint at hidden topology. Until then, wormholes remain a tantalizing what-if, reminding us that the universe's expansion might be even weirder than we've dared to imagine. Black holes, those cosmic vacuum cleaners lurking at the heart of galaxies, may be hiding a secret that rewrites dark energy's origin story. Recent studies reveal a startling correlation. The growth spurts of supermassive black holes align eerily with the universe's acceleration eras, as if these gravitational monsters are somehow fueling the expansion. Imagine pouring water into a balloon while someone simultaneously inflates it, except here the water is black hole mass and the inflation is spacetime itself stretching faster. The data paints a provocative picture. When astronomers compared black hole activity across cosmic time using X-ray surveys like Chandra and optical catalogs, they noticed two striking peaks, one around 11 billion years ago when quasars blazed brightest, and another coinciding with dark energy's takeover 5 billion years back. Graph these epochs alongside the universe's expansion rate, and the overlap raises eyebrows. Could black holes, traditionally seen as gravity's ultimate manifestation, actually be cosmic expansion engines in disguise? The mechanism proposed is as elegant as it is radical. As black holes consume matter and merge, their event horizons grow. But according to general relativity, the space inside a black hole's volume becomes disconnected from our universe's spacetime. Some theorists argue this missing space must be counterbalanced by the creation of new space elsewhere, like cosmic accounting keeping the books balanced. The math suggests every cubic light-year swallowed by a black hole's singularity could trigger a proportional expansion of spacetime outside it. It's as if the universe compensates for black holes' infinite curvature by stretching the rest of itself a little more. Support comes from an unexpected corner: black hole thermodynamics. When matter falls past the event horizon, it increases a black hole's entropy, a measure of disorder. But in the 1970s, Jacob Bekenstein and Stephen Hawking showed black hole entropy is proportional to its surface area, not volume. This holographic property implies black holes store information on their boundaries, not their interiors. If new space emerges to preserve this informational balance, it could manifest as dark energy's repulsive push. Visualize a black hole as a knot in spacetime. Tighten the knot, and the surrounding fabric stretches to compensate. Critics highlight glaring questions. If black holes drive expansion, why don't dwarf galaxies with smaller black holes show different expansion rates? And how do rogue black holes wandering between galaxies factor in? Proponents counter that only supermassive black holes, those weighing millions to billions of suns, have enough gravitational heft to influence cosmology. Their growth during galaxy mergers could release cascades of gravitational waves, subtly altering the vacuum energy around them in ways we're just beginning to model. The most tantalizing clue lies in elliptical galaxies. These ancient, quiescent galaxies host overweight black holes that stopped growing billions of years ago precisely when dark energy became dominant. Coincidence or evidence of a handoff where black holes seeded the expansion force we now attribute to dark energy? Future gravitational wave observatories like LISA could detect mergers from this critical era, testing whether space-time itself rippled differently as black holes transition from active feeders to dark energy's silent partners. Whether this theory holds or collapses under scrutiny, it forces a profound re-evaluation of cosmic constituents. Black holes might not just be byproducts of galaxy formation. They could be architects shaping the universe's destiny from the shadows, their insatiable appetites and cryptic thermodynamics woven into the fabric of expansion itself. The universe's finale isn't just one predetermined ending. It's a menu of cosmic catastrophes, each more dramatic than the last, all dictated by how dark energy behaves in the coming eons. Picture a cosmic clock ticking toward oblivion where the hands move at speeds we can barely calculate. On one end lies heat death, the slowest and most chilling option. Galaxies drift apart until each star burns out. Black holes evaporate into Hawking radiation, and the universe becomes a frozen graveyard near absolute zero. Time itself may lose meaning when there are no events left to measure. Yet this isn't the only possibility scribbled in the equations. If dark energy weakens over time, gravity could stage a comeback, reversing expansion in a spectacular big crunch. Imagine all galaxies rushing back together, space collapsing like a deflating balloon. Temperatures soar until atoms themselves disintegrate, culminating in a singularity mirroring the Big Bang, a cosmic cycle where the end becomes another beginning. But there's a twist. Quantum effects near the crunch could spawn an entirely new universe with different physical laws, like hitting the reset button on reality. The most violent finale, the Big Rip we explored earlier, a phantom energy-powered shredding of space-time where not even atomic bonds survive. Timelines for this scenario vary wildly based on dark energy's equation of state. Conservative models place it 22 billion years in the future, while extreme phantom energy versions suggest it could happen in as little as a few 100 million years if acceleration spikes unexpectedly. Then there's vacuum decay, an existential wild card where our universe's quantum fields suddenly drop to a lower energy state. Like a bubble of true vacuum expanding at light speed, this would rewrite physics in its wake, annihilating everything from galaxies to subatomic particles without warning. Theoretically, this could be triggered at any moment by a random quantum fluctuation anywhere in space. Comparative timelines reveal stark contrasts. Heat death unfolds over googles of years, while the Big Rip's timeline resembles a countdown clock. Cosmologists visualize these scenarios using phase diagrams where the fate hinges on dark energy's pressure-to-density ratio W. If W equals -1 exactly, we get the cosmological constant's endless expansion. Dip below -1 and phantom energy guarantees the rip. Nudge it higher and gravity might eventually win. Current data clusters around -1, but error bars leave room for surprises. The most haunting possibility, eternal inflation's multiverse, where our entire cosmos is just one bubble among infinite others, some collapsing, some ripping apart, others cycling endlessly. In this view, there is no universal end, just an infinite tapestry of cosmic experiments, each playing out its destiny according to local rules we'll never fully see. Future gravitational wave detectors could settle debates by measuring primordial ripples for signs of past collisions with other universes. What makes these scenarios so gripping isn't just their scale, it's how they force us to confront the limits of prediction. All our models break down near singularities or at temperatures approaching infinity. Perhaps the universe's ultimate joke is that its ending, like its beginning, will forever remain just beyond our grasp. Until then, we're left staring at the equations, tracing their curves into the inky blackness of deep time, wondering which path the cosmos will choose. From galaxies fleeing faster than light to black holes possibly fueling cosmic acceleration, the universe's expansion is packed with revelations that defy intuition. Who could have imagined that empty space itself holds a repulsive force strong enough to tear apart future galaxies, or that our entire universe might be one bubble in an infinite multiverse? Even now, the Hubble tension gnaws at cosmology's foundations, hinting that our measurements of reality might be missing something profound. Dark energy's true nature remains a mystery, whether it's vacuum fluctuations, evolving fields, or a sign that gravity itself plays by different rules on cosmic scales. And let's not forget the haunting possibility that constants like the fine structure constant might not be constant at all, subtly shifting over eons. The most humbling lesson: for all our telescopes and equations, we've barely scratched the surface. Every answer peels back another layer of questions. Are we living in a holographic projection? Is the acceleration we measure skewed by our place inside a cosmic void? Could phantom energy one day shred spacetime itself? The universe refuses to fit neatly into our models, and that's what makes this journey so thrilling. So as we zoom out past the moon, past the Milky Way, past the shimmering filaments of the cosmic web, remember this: you're not just watching the universe expand. You're witnessing the greatest detective story of all time, where the clues are written in starlight and the stakes are the very nature of reality. If your mind is buzzing with questions, you're not alone. Hit subscribe to join us as we chase the next cosmic revelation, because the universe's secrets are far from finished. Until then, keep looking up. The night sky isn't just a view, it's an invitation to